January 28th, 2026, a 30-year-old astronomer named Rohan Naidu posted a single image to social media. It showed a faint red smudge, barely a handful of pixels across, pulled from the infrared detectors of the James Webb Space Telescope. That smudge is a galaxy called MOM-Z14. Its light left it 280 million years after the Big Bang, which means the universe was roughly 2% of its current age when this thing existed. To put that in perspective, if the entire history of the cosmos were compressed into a single calendar year starting January 1st, MOM-Z14 was already shining by January 7th, 1 week into everything. And it should not exist. Not in any metaphorical sense. Not in any popular science, gee whiz. Look how surprising the universe is kind of way. MOM-Z14 is 182 times brighter than the best models of the early universe predicted anything could be at that distance. The range on that number, accounting for statistical uncertainty, runs from 77 times to 511 times. Even the most conservative reading says this galaxy is almost 2 orders of magnitude more luminous than our physics allows, and it is not alone. For 3 years now, the James Webb Space Telescope has been finding galaxies in the infant universe that are too bright, too massive, too chemically mature, and far, far too numerous. Every single new discovery has made the problem worse. Not better. Worse. Xuejin Shen, a colleague of Naidu's at MIT, put it about as plainly as a scientist can. There is, he said, a growing chasm between theory and observation related to the early universe. This is the story of that chasm. How it opened, how it widened, and why, 3 years into the most powerful space telescope ever built, nobody has been able to close it. Because the question hanging over all of this is not simply whether we got the details wrong about how the first galaxies formed. The question is whether we understand the early universe at all. That is what we are going to try to figure out. To understand why MOM-Z14 is such a problem, you need to understand what the universe was supposed to look like at 280 million years old. And the word supposed is doing a lot of heavy lifting in that sentence, because the prediction was not vague. It was not hand-wavy. Cosmologists had spent decades building a model of the universe that is, by any honest measure, one of the most successful theoretical frameworks in the history of science. It is called Lambda-CDM, short for lambda cold dark matter, and it describes a universe made of roughly 5% ordinary matter, 27% cold dark matter, and 68% dark energy. That model matches the cosmic microwave background radiation to extraordinary precision. It predicted the large-scale structure of the cosmic web. It explains the observed expansion rate, the abundance of light elements from Big Bang nucleosynthesis, and the statistical distribution of galaxy clusters across billions of light years. Lambda-CDM is not some back-of-the-envelope guess. It has been tested against observation after observation after observation for more than 2 decades, and it has passed nearly every single time. And Lambda-CDM makes a very specific prediction about what the early universe should look like. The prediction is hierarchical assembly. Small things form first. Dark matter clumps into tiny halos. Ordinary gas falls into those halos and slowly cools. Stars begin to form, but slowly, inefficiently, converting only about 2 to 10% of the available gas into stars, because supernova explosions keep blowing the rest of the material out of the galaxy before it can collapse. Those small proto-galaxies then merge, gradually building bigger structures over hundreds of millions and eventually billions of years. The whole process is bottom-up. You start small and you build toward big. Michael Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, who has become one of the most important voices in this entire saga, distilled the prediction into a single sentence that has become famous in the field. "There are no big things at early times," he said. "It takes a while to get to big things." He then offered an analogy that became the defining metaphor for everything that followed. Finding massive bright galaxies just a few 100 million years after the Big Bang, he said, would be akin to finding a fossilized rabbit in Precambrian strata. In paleontology, complex animals did not appear in the fossil record for billions of years after life began. If you found a rabbit fossil in rocks that predate even single-celled organisms, it would not just be surprising. It would break your model of how life develops. It would mean something fundamental about evolution was wrong. That is exactly what JWST found. Not one rabbit, dozens of them. But we are getting ahead of ourselves, because the story does not start with MOM-Z14. It starts 3.5 years earlier, on a summer night in Washington. On July 11th, 2022, President Joe Biden stood at a podium in the White House and revealed the first deep-field image from the James Webb Space Telescope. The image showed galaxy cluster SMACS0723, a gravitational lens that magnifies the light from far more distant galaxies behind it. It was, by any standard, a technical triumph. JWST had been in development since 1996. Its 6.5-meter gold-plated beryllium mirror, its sunshield the size of a tennis court, its cryogenic instruments operating at -233 degrees Celsius. All of it had been designed to do one thing above all else. See the first galaxies. See what came out of the darkness after the Big Bang, after the cosmic microwave background was released 380,000 years in, after the universe cooled and went dark, and there was nothing but neutral hydrogen gas slowly falling into invisible dark matter scaffolding. JWST was supposed to find the dim, small, fragile first galaxies tentatively flickering into existence in that primordial darkness. Within days of that first image going public, multiple teams independently scouring the data realized something was very wrong. The galaxies were not dim. They were not small. They were, as Rohan Naidu would later put it, just so stupidly bright, and they just stood out in two separate early release programs called GLASS and SEERS. Teams found galaxy candidates at staggering distances. One of them, initially designated GLASS Z13, appeared to sit at a redshift of approximately 13, which would place it about 350 million years after the Big Bang. It was found independently by two teams on two continents, Naidu and collaborators at Harvard and MIT, and Marco Castellano's group at INAF in Rome. The object was bright, far brighter than anything Lambda-CDM said should exist at that distance, and it was not the only one. Another team, led by Stephen Finkelstein at the University of Texas at Austin, found a candidate in CEERS data that appeared even closer to the Big Bang, They called it Maisie's Galaxy, and the name has a story behind it that matters for reasons beyond the astronomy. Finkelstein found it on his daughter Maisie's 9th birthday. She had been asking him to name a galaxy after her, and he had told her they were not really allowed to do that. But because it turned up on her birthday, he just started calling it Maisie's Galaxy, and the name stuck. That small human moment, a father at his desk, his daughter's birthday, a dot of light from 400 million years after the creation of the universe, became one of the earliest threads in a story that would consume the entire field of observational cosmology for the next 3 years. But there was a problem with all of these discoveries, and it was a serious one. Every single one of them was based on photometric redshifts, and photometric redshifts can lie. Here is what that means. When you look at a very distant galaxy, the expansion of the universe stretches its light toward longer wavelengths. The farther away the galaxy, the more its light gets stretched, and the redder it appears. This stretching is called redshift, and it is measured by a number called Z. A galaxy at Z equals 14 means the universe has expanded by a factor of 15 since that galaxy emitted its light. Now, there is a specific feature in the light of every galaxy that astronomers exploit to measure this. Neutral hydrogen absorbs almost all ultraviolet light at wavelengths shorter than 121.6 nanometers, which is the Lyman alpha line. So when you look at a distant galaxy, there is a sharp cutoff in its spectrum. Everything bluer than Lyman alpha is missing, absorbed by all the neutral hydrogen between you and the source. This is called the Lyman break, and for a galaxy at Z equals 14, that break gets redshifted all the way out to about 1.8 micrometers in the near infrared, which is exactly the wavelength range where JWST's NIR-CAM instrument operates. Photometric redshifts work by taking images of a galaxy through a series of filters at different wavelengths and looking for that dropout. If a galaxy is visible in longer wavelength filters, but invisible in shorter ones, you can estimate where the Lyman break falls and therefore estimate the redshift. It is fast. It lets you survey large areas of sky efficiently, but it is also imprecise, with typical uncertainties of plus or minus 0.5 or more in redshift. And worse than that, it can be fooled. A galaxy that is not particularly distant, but has very strong emission lines, can mimic the broadband color signature of a Lyman break galaxy at much higher redshift. You think you are seeing something from 300 million years after the Big Bang, when you are actually seeing something from 1 billion years after the Big Bang that happens to have unusual spectral features. This is not a hypothetical concern. It is exactly what happened with one of the most dramatic early candidates in July 2022. The same frantic weeks when Glass Z13 and Maisie's Galaxy were being announced, a team led by Callum Donnan at the University of Edinburgh identified a candidate in Sears data with an estimated photometric redshift of 16.7. If real, that would have placed it just 235 million years after the Big Bang, deep in what cosmologists call the cosmic dark ages, before the first stars were even supposed to have finished forming. The number was extraordinary. It was also, as it turned out, completely wrong. When the spectroscopic data came back, the object designated CEERS-93316 was not at z equals 16.7. It was at z equals 4.9, a perfectly ordinary galaxy, about 1.1 billion years after the Big Bang, roughly 4 times closer than the photometric estimates suggested. It had strong emission lines that happened to mimic the color signature of a Lyman break at z equals 16 or 17. The galaxy was not impossible at all. It was a mirage. Finkelstein, whose team had flagged it, took the result in stride. It would have been really challenging to explain how the universe could create such a massive galaxy so soon, he told Space.com. So I think this was probably always the most likely outcome. CEERS 93316 became the poster child for why spectroscopic confirmation is essential. You cannot trust a photometric redshift alone, especially at the extremes. And in August 2022, barely a month after JWST's first images went public, Michael Boylan-Kolchin published an influential single-author paper arguing that even the surviving galaxy candidates, the ones that had not yet been debunked, could already be in significant tension with Lambda-CDM. His argument was mathematical, and it was devastating. To explain the stellar masses implied by these candidates, you would need to convert nearly 100% of available baryonic gas into stars. The expected efficiency was 2 to 10%. Getting to 100% would require shutting off every feedback mechanism that regulates star formation, every supernova that heats gas and blows it out of a galaxy, every source of turbulence and radiation pressure that prevents gas clouds from collapsing. It was physically unreasonable. Something had to give. But Boylan-Kolchin was careful. He emphasized that these were photometric candidates. The tension was real but provisional. Everything depended on what happened when the spectrographs were pointed at these objects and the actual redshifts were nailed down. If most of the candidates turned out to be CEERS 93316 style mirages, the crisis would evaporate. If they turned out to be real, the crisis would be profound. So the field held its breath, and then the spectra started coming back. In December 2022, the JD survey released its first spectroscopic results. JD's, the JWST Advanced Deep Extragalactic Survey, is the largest observing program from JWST's first cycle, consuming roughly 770 to 800 hours of telescope time. It is co-led by Daniel Eisenstein at Harvard and Andrew Bunker at Oxford, and it targets 2 of the most thoroughly studied patches of sky in astronomy, the Goods South and Goods North fields. These are the same regions where Hubble spent weeks staring at apparently empty sky and found galaxies all the way down. JWST went back to those same patches with instruments that are orders of magnitude more sensitive in the infrared, and JADES combined deep NIR-CAM imaging in 9 filters with thousands of spectra from NIR-SPEC. The results were immediate and unambiguous. JD's confirmed 4 galaxies at redshifts greater than 10, including one designated JD's GSZ 13.0 at Z equals 13.20, roughly 325 million years after the Big Bang. That was the new spectroscopic distance record. And the critical point was not just that one object existed at that distance. The critical point was the sheer number of confirmed galaxies at Z greater than 10. There were more of them by a substantial margin than any pre-JWST prediction had anticipated. The model said the number of galaxies should decline steeply above Z equals 9. JWST found a much shallower decline. There were simply far more bright galaxies in the early universe than anyone expected. The mirages were real, yes. CEERS 93316 proved that. But the miracles were also real, and there were a lot more miracles than mirages. Roughly 1 in 10 candidates turned out to be a misidentification. The other 9 survived scrutiny. The problem was not going away. And then, in February 2023, the problem got much stranger. A team led by Andrew Bunker pointed JWST's NIR spec instrument at a galaxy called GN-Z11. This was not a new discovery. GN-Z11 had been found in 2016 by Pascal Oesch using the Hubble Space Telescope, and for half a decade it held the record as the most distant known galaxy at a redshift of about 11.1, but Hubble could only do so much. JWST could take a proper spectrum, decompose the light into its full set of wavelengths, and read the chemical fingerprints embedded in it. What Bunker's team found was genuinely alarming. First, the refined redshift came in at Z equals 10.603, which corresponds to about 430 million years after the Big Bang. That was expected. But the spectrum also revealed that GN-Z11 hosts a supermassive black hole with a mass of roughly 2 million solar masses. That made it the most distant active galactic nucleus ever confirmed, a 2 million solar mass black hole, 430 million years into the universe. Growing a black hole that large that quickly is itself a major theoretical challenge. But the real shock was not the black hole. The real shock was the nitrogen. Bunker's team detected 2 emission lines in GN-Z11 spectrum that should not have been there. They were the semi-forbidden nitrogen lines N4 at 1486 angstroms and N3 at 1748 angstroms. And the nitrogen abundance was not just elevated, it was more than 4 times the solar value. The ratio of nitrogen to oxygen, measured as the logarithm of N over O, came in at negative 0.24 or higher. For reference, the solar value is negative 0.86. GN-Z11 had roughly 4 times more nitrogen relative to oxygen than the Sun, and it existed in a universe that was barely 400 million years old. To understand why that is such a problem, you need to understand how nitrogen gets made. And this is where the story moves from surprising to potentially paradigm-breaking. Every element heavier than lithium was forged inside a star. That is one of the foundational results of 20th century astrophysics, and it remains true. But not all elements are forged in the same way or on the same timescale. Oxygen is an alpha element. It gets made in the cores of massive stars, stars that live fast and die young, burning through their fuel in just 3 to 10 million years before exploding as core collapse supernovae and scattering their newly forged oxygen into the surrounding gas. So oxygen enrichment is fast. Give a galaxy a burst of massive star formation, and within 10 million years, you have fresh oxygen in the interstellar medium. Carbon is somewhat slower, but still relatively fast, coming from both massive stars and intermediate mass stars on timescales of tens of millions of years. But nitrogen is different. Nitrogen-14 is produced primarily through the CNO cycle, a particular set of nuclear reactions that occurs in stars more massive than about 1.3 solar masses. In the CNO cycle, pre-existing carbon-12 acts as a catalyst. capturing protons through a chain of reactions. The critical step is the reaction where nitrogen-14 captures a proton to produce oxygen-15. That reaction has a very small cross-section, meaning it happens slowly, and the result is that nitrogen-14 accumulates as a bottleneck in the cycle. It is the most abundant CNO nucleus at equilibrium, precisely because it is hard to destroy. But here is the essential point. Nitrogen is what chemists call a secondary element. Its production depends on having pre-existing carbon and oxygen to serve as catalysts in the CNO cycle. You cannot make nitrogen from scratch. You need carbon first, and the primary pathway for getting nitrogen out of stars and into the gas between stars is through the winds of asymptotic giant branch stars, AGB stars, which are intermediate mass stars in the late stages of their evolution. The main sequence lifetimes of the relevant AGB star progenitors run from about 100 million years for the more massive ones to several billion years for the less massive ones. So building up nitrogen, especially building it up to supersolar levels, traditionally requires multiple generations of stars. First, you need massive stars to make and distribute carbon and oxygen. Then you need intermediate mass stars to process that carbon and oxygen through the CNO cycle and release the resulting nitrogen. The whole sequence takes hundreds of millions of years at minimum, and at 430 million years after the Big Bang, there's barely been time for one generation of massive stars to live and die. 2 generations stretches credulity. Multiple generations of intermediate mass AGB stars enriching the gas with nitrogen to 4 times the solar abundance is, on the face of it, impossible. There simply has not been enough time. This is why Bunker's detection of nitrogen in GN-Z11 sent shockwaves through the field. The brightness problem was already alarming. The abundance problem was worse. You could potentially explain away bright galaxies by tweaking star formation physics, adjusting feedback models, invoking bursty episodes that temporarily boost luminosity. But the nitrogen is a chemical clock. It records a history of stellar evolution that takes a certain minimum amount of time. And the clock says, more time has passed in these galaxies than the universe has actually existed. Think about that. The chemistry inside these galaxies implies a history that is longer than the age of the universe at the time we are observing them. Now, nobody was ready to throw out Lambda-CDM over nitrogen emission lines in a single galaxy. GN-Z11 could have been unusual. It could have had a peculiar formation history. There were proposed explanations that, while exotic, stayed within the boundaries of known physics. The most prominent one came from Chiaki Kobayashi at the University of Hertfordshire and Andrea Ferrara, who proposed that GN-Z11 might have experienced intermittent, bursty star formation. In their scenario, a first episode of intense star formation occurs early, producing massive stars that enrich the gas with carbon and oxygen. Then there is a roughly 100 million year quiescent phase where very little new star formation happens. Then a second intense burst occurs, and in that second burst, very massive Wolf-Rayet stars, up to about 120 solar masses, go through a brief phase where their winds are enormously enriched in nitrogen from CNO cycle processing. For less than 1 million years, those winds temporarily boost the nitrogen abundance in the surrounding gas. If you happen to observe the galaxy during that narrow window, you would see exactly the kind of supersolar nitrogen signature that Bunker's team found. Kobayashi put it precisely. "The galaxy is not telling us about an unusual star," she said, "but an unusual episode of galaxy life." Her explanation had the virtue of keeping the physics conventional. No new particles, no new forces, no modifications to cosmology, just an unusual but not impossible sequence of star formation events. But there was another explanation, one that was more exotic and, as it turned out, more prescient. In 2023, Corinne Charbonnel and collaborators published a paper in Astronomy and Astrophysics proposing that the nitrogen pattern could be produced by supermassive stars, objects exceeding 1,000 solar masses, forming through runaway collisions in extremely dense proto-globular cluster environments. Stars that massive would burn hydrogen at temperatures high enough for the hot CNO cycle to operate at full efficiency, naturally producing the observed nitrogen to oxygen and nitrogen to carbon ratios. They would be unlike anything we have ever directly observed. They would be unlike anything that exists in the universe today. But the chemical fingerprint they would leave behind matched what Bunker found in GN-C11. And there was an intriguing coincidence: the abundance patterns. Charbonnel calculated for these hypothetical supermassive stars matched the abundance patterns observed in the oldest stars in the Milky Way's globular clusters. Those clusters are the most ancient stellar structures in our galaxy, thought to have formed in the earliest epochs of cosmic history. If supermassive stars existed in the early universe and produced the nitrogen anomaly, the connection to globular clusters would mean we were looking at the actual birth conditions of structures that still exist in our own galaxy 13 billion years later. At the time, this was speculative. GNZ11 was one galaxy. The nitrogen detection, while solid, was from a single object, but Bunker's discovery meant the spectrographs were now tuned to look for nitrogen wherever JWST pointed at the early universe. The theoretical community, meanwhile, was working on the broader brightness problem with increasing urgency. In the 18 months following JWST's first images, a constellation of papers appeared proposing mechanisms to reconcile the impossibly bright early galaxies with Lambda-CDM. The proposals fell into three broad categories, and understanding all three matters because the story of the next 2 years is the story of each one failing to fully explain what JWST kept finding. The first category was bursty star formation. This was the most conventional explanation, and it had a significant advantage. A group at Northwestern led by Guoqiao Sun, Claude-André Fauquer-Giguère, and Andrew Wetzel had been running cosmological simulations called FIRE, and crucially, they had run them before JWST launched. The FIRE simulations included detailed models of how supernova feedback creates cycles of intense star formation, followed by quiet periods. When they checked their pre-launch predictions against JWST's observed luminosity functions at z greater than 10, the match was surprisingly good. The key insight was that brightness is not the same as mass. As Fauquer-Giguère explained, most of the light in a galaxy comes from the most massive stars. Because more massive stars burn at a higher speed, they are shorter lived, so the brightness of a galaxy is more directly related to how many stars it has formed in the last few million years than the mass of the galaxy as a whole. A galaxy caught in the middle of a starburst looks far brighter than its total stellar mass would suggest. Catch it during a quiet period, and it fades dramatically. If early galaxies were burstier than later ones, the average brightness at any given time would be much higher than a smooth star formation model predicts. This was genuinely encouraging. It meant you could explain the brightness without breaking Lambda-CDM. The galaxies were not necessarily more massive than predicted. They were just caught at their brightest moments. But there was a catch. Bursty star formation could explain the luminosity. It could not explain the chemistry, and it could not explain the sheer number density. Even with burstiness factored in, there were still too many galaxies at these distances. The second category of explanation was active galactic nuclei, and it came with its own partial vindication. Catherine Chorosky and Stephen Finkelstein at the University of Texas published a study in 2024 showing that many of the so-called impossibly massive early galaxies were actually what the field had started calling little red dots. These are compact red objects that turn out to contain active galactic nuclei, accreting supermassive black holes whose radiation makes the host galaxy appear far brighter and more massive than starlight alone would produce. When Chorosky and Finkelstein carefully removed the AGN-contaminated objects from their galaxy samples, the remaining galaxies fell much closer to Lambda-CDM predictions. The massive galaxies that had been causing the most dramatic headlines were, in many cases, not as massive as they appeared. Their brightness was being inflated by black hole accretion, not stellar mass. Finkelstein was characteristically direct about it. There is no crisis in terms of the standard model of cosmology, he said. But even with the little red dots removed, the problem did not disappear. It shrank, but it persisted. After AGN contamination was accounted for, there were still roughly twice as many massive galaxies in the early universe as standard models predicted. A factor of 2 is not a catastrophe on the scale of a factor of 182, but it is a real statistically significant discrepancy, and it was stubbornly resistant to further corrections. The third category was modifying the initial mass function. The initial mass function, or IMF, describes the relative proportion of high-mass and low-mass stars produced when a cloud of gas collapses and forms a new generation of stars. In the local universe, the IMF follows a well-characterized distribution with far more low-mass stars than high-mass ones. But if the IMF in the early universe was tilted toward producing proportionally more massive stars, those additional bright massive stars would boost the total UV luminosity without requiring more total stellar mass. Ann Hutter and collaborators published a study in 2025 showing that a top-heavy IMF could enhance UV luminosity by up to 2.6 magnitudes. This seemed promising until January 2026, when a study led by Chloe Cheng using data from the JWST IMF-ERNO program threw a wrench directly into the gears. Cheng's team looked at the descendants of the early impossible galaxies, objects that had evolved from those early epochs to somewhat later times, and found that they actually had an excess of low-mass stars. Their IMFs were bottom-heavy, not top-heavy, and a bottom-heavy IMF means more total stellar mass is needed to produce the same amount of light. Instead of solving the problem, the IMF measurement actually amplified the tension by a factor of 3 to 4. So by early 2026, the situation looked like this. Bursty star formation explained the brightness, but not the chemistry or the number density. A GN contamination explained some of the apparent excess, but left a factor of 2 discrepancy. Top-heavy IMFs were contradicted by direct observation. Each proposed solution handled one facet of the problem, while leaving others untouched or actively worsened. No single coherent model could account for everything JWST was finding. And then the record broke again and again. And the chasm that Shui-Jian Shen described did not close. It widened. On May 30th, 2024, a team led by Stefano Carniani at the Scuola Normale Superiore in Pisa, Italy, published the spectroscopic confirmation of a galaxy that obliterated the previous distance record. It was called JADESGS Z140, and it sat at a spectroscopic redshift of 14.32, later refined to 14.18 by the ALMA radio telescope array in Chile. That placed it roughly 290 million years after the Big Bang, 70 million years closer to the beginning of everything than the previous record holder. And it was not a small, faint, fragile, protogalactic fragment of the kind Lambda-CDM predicted. It stretched across more than 1,600 light years, far too extended and resolved to be a quasar or an active nucleus mimicking a galaxy. Its stellar mass ran into the hundreds of millions of solar masses. This was a genuine galaxy containing hundreds of millions of stars, physically large, already assembled into a coherent structure, existing in a universe that was barely 2% of its current age. Carniani's own reaction captures the mood. "I was astonished by the unexpected results," he said, "because they opened a new view on the first phases of galaxy evolution. But astonishment had been the default state in this field for 2 years by that point. What made JADESGS Z140 different from the earlier candidates was not just the record-breaking distance. It was what came next, because JADESGS Z140 became the target of one of the most ambitious follow-up campaigns in modern astronomy. Teams pointed JWST at it again. They pointed ALMA at it, and they threw everything they had at this object because it was, at the time, the single most distant confirmed galaxy in the history of human observation. And they wanted to know everything it could tell them about the conditions just after cosmic dawn. The result from ALMA, published in March 2025, was the detection of oxygen, the most distant detection of that element ever made. And the oxygen abundance was roughly 10 times higher than models predicted for a galaxy at that distance and age. Sander Skos, a member of the team, offered an analogy that cut through the jargon. "It is like finding an adolescent where you would only expect babies," he said. The galaxy was chemically aged in a way that implied extensive prior stellar processing. Multiple generations of stars had to have lived and died and scattered their processed material into the surrounding gas before the gas was recycled into the stars we were now observing. The oxygen clock, like the nitrogen clock in GN-Z11, was running ahead of the universe's actual age. Now, it is worth pausing here to appreciate the cumulative weight of what had happened in the 22 months between JWST's first image and the JADES-GS-Z14-0 oxygen detection. The initial reaction in July 2022 was cautious excitement. The photometric candidates were tantalizing but unconfirmed. CEERS-93316, showed that mirages were real. Boylan-Colchin's paper established the theoretical stakes, but left room for the problem to dissolve once spectra came in. Then the spectra came in, and most candidates survived. Then GNZ11 revealed nitrogen that should not exist. Then the theoretical response fractured into partial explanations that each solved a piece of the puzzle, while leaving the rest unsolved. Then the distance record shattered, and the new record holder turned out to have oxygen enrichment 10 times beyond predictions. Each step made the next one more alarming, not because any single result was individually inexplicable, but because the combination of results was becoming increasingly difficult to accommodate within any single framework. Brightness plus number density plus chemical maturity plus structural coherence at progressively earlier times in the universe. The problem was not getting simpler. It was growing new dimensions. And the human story behind these discoveries is itself part of what makes them remarkable, because the connections between the people involved span decades and continents in ways that mirror the connections the telescopes were revealing across cosmic time. Consider Rohan Naidu, the man who would confirm MOM-Z14 as the most distant galaxy ever observed, grew up in Hyderabad, India. At 18, in what he calls a Bollywood-esque plot twist, he dropped out of engineering school, bought the first plane ticket of his life, and joined the founding class of just 150 students at Yale NUS College in Singapore, which was, at that time, Asia's first liberal arts college. He had no background in astronomy. He discovered the field while studying blazars in the Chilean Andes as part of a project supervised by Charles Bailyn. From there, he went to Yale as an exchange student, where he worked with a Swiss astronomer named Pascal Oesch. That name matters. Pascal Oesch, now at the University of Geneva, was the person who discovered GN-Z11 with the Hubble Space Telescope in 2015 and 2016. For half a decade, GN-Z11 held the distance record. Oesch had built his career on pushing the redshift frontier, and when JWST launched, he designed a survey specifically intended to determine whether the flood of ultra-high redshift photometric candidates were genuine or artifacts. He called it the Mirage or Miracle Survey, MOM for short. And the person he chose as his co-principal investigator was the former undergraduate exchange student who had worked in his group at Yale, Rohan Naidu. The relationship between Oesch and Naidu, from mentor and student to co-investigators leading one of the most consequential surveys in the history of observational astronomy, is itself a story about how scientific discovery flows through human relationships across generations. Oesch found GN-Z11 with Hubble. Bunker's team at Oxford revealed its impossible nitrogen with JWST Naidu, trained in the lineage of Oesch's research program, designed the survey that would find the object that broke GN-Z11's record and deepened the nitrogen mystery beyond anything Bunker had seen. And it was not just Naidu and Oesch. Consider Andrew Bunker, whose nitrogen detection in GN-Z11 opened the chemical chapter of this entire saga. Bunker had been on the European Space Agency's NIR Spec Instrument Science team since 2005. That is over 2 decades of work on a single instrument before JWST even launched. 20 years of meetings, design reviews, testing, calibration, all for the instrument that would eventually decompose the light of the earliest galaxies into individual spectral lines and reveal what elements were present. When NIR spec finally pointed at GNZ11 and those nitrogen lines appeared on his screen, Bunker was seeing the payoff of a career-long investment in a machine that had not yet existed when he started working on it. In 2026, he was awarded the Herschel Medal of the Royal Astronomical Society for outstanding observational astrophysics. Or consider Boylan-Kolchin, whose Precambrian rabbit paper in August 2022 anticipated the crisis before most of the data was even in. Boylan-Kolchin is a theorist, not an observer. He did not find any galaxies. He did the math on what the early candidates implied for Lambda-CDM and published a paper that essentially said, if these are real, we have a serious problem. He has over 25,000 citations on Google Scholar. He has become the field's most quotable voice on whether JWST has broken cosmology, and his assessment has remained remarkably consistent and remarkably measured over 3 years. Those are the best problems, he has said, of the discrepancies, because no matter what you get, the answer is interesting. That intellectual honesty, the willingness to live with uncertainty rather than prematurely picking a side, runs through the entire story. The theorists proposing bursty star formation genuinely believe they can explain a large portion of the observations. The observers finding impossible chemistries genuinely believe the data is solid. Nobody is fabricating a crisis, and nobody is dismissing one. The community is doing what good science does. It is arguing rigorously and with data about what the universe is trying to say. But by mid-2025, the universe had something new to say, and it said it through MOM-Z14. The Mirage or Miracle Survey had been designed with exactly this moment in mind. Oish and Naidu knew from CEERS-93316 that photometric candidates could be mirages. They also knew from the JADES confirmations that many candidates were genuine miracles. So, MOM was built as a spectroscopic filter. The survey covers approximately 350 square arc minutes across two of the most well-studied extragalactic fields, the Cosmos field and the UDS field. The strategy was straightforward. Find photometric candidates at Z greater than 10 using deep NIRCam imaging in 10 filters from F090W through F444W. Then point NIR spec prism spectroscopy at the most promising ones at R equals 100 resolution to get definitive spectroscopic redshifts. Mirage or miracle? Binary outcome. Are these objects real or not? On April 16th, 2025, the telescope pointed NIR spec at a candidate in the survey and integrated for 4.4 hours. The spectrum came back clean. A sharp Lyman alpha break consistent with Z equals 14.44 plus 5 rest frame ultraviolet emission lines detected at roughly 3 sigma significance. MOM-Z14 was real, not a mirage, a miracle. The paper, titled A Cosmic Miracle, a remarkably luminous galaxy at Z spec equals 14.44 confirmed with JWST, listed Naidu as lead author with 45 co-authors. It was first posted to Ahakankshav on May 16th, 2025, and published in peer-reviewed form in the Open Journal of Astrophysics, Volume 9, on January 28th, 2026. NASA issued its science release the same day. The numbers are stark. MOM-Z14 sits at a spectroscopic redshift of 14.44 plus or minus 0.02. Its light was emitted 280 million years after the Big Bang. Some sources specify 282 million years. It has traveled 13.53 billion years to reach us, and because the universe has been expanding the entire time, its current co-moving distance is 33.8 billion light-years. The galaxy itself is extraordinarily compact, with an effective radius of just 74 parsecs, roughly 240 light-years across. That is about 400 times smaller than the Milky Way. Its stellar mass is approximately 100 million solar masses, comparable to the Small Magellanic Cloud, one of our galaxy's tiny satellite companions, and its UV luminosity is MUV equals negative 20.2, which for something at that distance and that age is staggeringly bright. But the number that captures the true scale of the problem is not any property of MOM-Z14 itself. It is the number density. The MOM survey implies that bright galaxies at Z equals 14 to 15 are 182 times more numerous than the consensus pre-JWST models predicted. The uncertainty range runs from 77 to 511 times. Even at the low end, you are looking at nearly 2 orders of magnitude more galaxies than the physics said should exist. This is not about one anomalous object. This is about the statistical abundance of objects like it. MOM-Z14 is not a freak. It is a representative of a population that should not be there, and the nitrogen was back. Among those 5 emission lines detected in MOM-Z14 spectrum, one of them was the semi-forbidden N4 line, the same nitrogen feature that Bunker had found in GN-Z11. And the nitrogen abundance was even more extreme than before. MOM-Z14 shows a supersolar nitrogen to carbon ratio of N/C greater than 1 at 280 million years after the Big Bang. In a galaxy where there has been time for, at absolute most, 1 generation of massive stars to form, burn through their fuel, and die. The nitrogen clock is not just running ahead of the universe. It is running ahead by an amount that defies every conventional explanation. Naidu's team identified something they called a size chemistry bimodality in galaxies at redshifts above 10. The pattern is striking. Compact galaxies, the small dense ones like MOM-Z14, GN-Z11, and another object called Glass-Z12, are strong nitrogen emitters. Extended galaxies, the physically larger ones like JD's GSZ140, show weak or absent nitrogen. The compact sources with their extreme nitrogen abundances have chemical fingerprints that are remarkably similar to the oldest stellar populations in the Milky Way's globular clusters, the ancient star clusters that have been orbiting our galaxy since its earliest days. And the globular cluster abundance patterns have long been a puzzle in their own right, because they seem to require the existence of luminous, supermassive stars exceeding 1,000 solar masses, stars that no longer exist anywhere in the observable universe. The MOM-Z14 paper favors this supermassive star explanation. The language in the paper is careful, but the implication is enormous. We may be directly witnessing the formation of such stars in dense clusters, connecting galaxy evolution across the entire sweep of cosmic time. If that interpretation holds, then MOM-Z14 is not just the most distant galaxy. It is a window into a mode of star formation that has been extinct for 13 billion years. one that built the very structures, the globular clusters that still orbit our home galaxy today, we would be looking at our own deep ancestry. And on that same day, January the 28th, 2026, while the astronomical community was absorbing MOM-Z14, a completely different paper landed in the journal Nature with a completely different kind of impossibility. Because the early universe was not just making galaxies too fast, it was building structures too fast. The paper described JWST, a protocluster at Redshift 5.68, roughly 1 billion years after the Big Bang. A protocluster is a massive structure of galaxies in the process of collapsing under gravity to form what will eventually become a galaxy cluster, one of the largest gravitationally bound structures in the universe. JADES-ID1 contains at least 66 galaxies identified by JWST, all gravitationally bound, with a total estimated mass of roughly 20 trillion solar masses. But the feature that made it genuinely unprecedented was not the galaxies. It was the gas. The Chandra X-ray Observatory, which has been staring at the same patch of sky as JWST in what is called the Chandra Deep Field South, the deepest X-ray observation ever conducted, detected a cloud of hot gas surrounding and embedding the protocluster. This gas, called the intracluster medium, had been heated to millions of degrees by gravitational shock waves as it fell inward toward the center of mass. Chandra measured a bolometric X-ray luminosity of 1.5 times 10 to the 44th ergs per second, with extended emission stretching out to about 125 kiloparsecs, roughly 400,000 light-years. Hot gas like this is the hallmark of a mature, collapsing megastructure. It is what you see in galaxy clusters in the nearby universe, structures that have had billions of years to assemble. It is emphatically not what you expect to see 1 billion years after the Big Bang. The lead author was Akos Bogdan at the Harvard-Smithsonian Center for Astrophysics, with 3 co-authors, Gerrit Schellenberger, also at Harvard-Smithsonian, and Kyung Lee and Christopher Consolis at the University of Manchester. Bogdan is known for combining JWST and Chandra data to make composite discoveries. He also led the discovery of UHZ1, the most distant X-ray quasar, at Z equals 10.1. On JADES-ID1, he was blunt. "We either got extremely lucky," he said, "or we are catching a region of the universe that grows unusually fast." Standard cosmological models predicted that protoclusters with hot gas embedding should not appear until 2 to 3 billion years after the Big Bang at the earliest. The previous record for an X-ray emitting protocluster was a roughly 3 billion years post-Big Bang. JADES-ID1 pushed that back by approximately 2 billion years. While a handful of protoclusters have been identified at higher redshifts without X-ray emission, notably one called A2744Z7P90D at Z approximately 7.9, about 650 million years after the Big Bang. None of those showed the hot gas that signals active gravitational collapse on a cluster scale. JADES-ID1 was different. It was not just a collection of galaxies that happened to be near each other. It was a collapsing megastructure, actively assembling, with the thermodynamic signature to prove it. Schellenberger framed the significance in terms of what it means for how we study the universe. It is very important to actually see when and how galaxy clusters grow, he said. It is like watching an assembly line make a car, rather than just trying to figure out how a car works by looking at the finished product. And Klaus Döhler, a cosmologist at LMU Munich, who was not involved in the study, articulated the stakes for fundamental physics. Either we learn something new about the complex interplay of various physical processes shaping the formation of galaxies, he said, or we learn there is indeed a flaw in our general background model of cosmology. That word, flaw, in the background model, meaning Lambda-CDM itself. 3 years into JWST, the possibility that had been theoretical was being stated out loud in Nature by external commentators, not as a fringe position, not as clickbait, as a legitimate reading of the evidence. So where does that leave us? The inventory of what JWST has found in 3 years is now extensive enough to summarize, and the summary is sobering. Galaxies at redshifts above 10 that are at least an order of magnitude brighter than predicted, measured across a sample of 88 galaxies at Z greater than 8.5. Galaxy number densities at Z-days equals 14 to 15 that are 182 times higher than consensus models. Stellar masses up to 1 billion to 10 billion solar masses at 500 to 700 million years, compared to predicted masses well below 100 million solar masses, star formation efficiencies that would need to reach 57 to 100% to match the observations, compared to the predicted 2 to 10%. Nitrogen enrichment to 4 times solar in a galaxy at 430 million years, and supersolar nitrogen to carbon ratios in a galaxy at 280 million years, implying chemical evolution timescales that exceed the actual age of the universe at the time of observation. A surprisingly high fraction of disk galaxies at 500 million to 2 billion years, including individual objects like the Big Wheel Galaxy at Z, approximately 3, that is 3 times larger than simulations predict, and a galaxy protocluster with hot X-ray emitting gas at 1 billion years, roughly 2 billion years earlier than models allow. No single theoretical framework explains all of this. Bursty star formation handles the brightness, but not the chemistry or structure formation. A GN contamination reduces the mass problem, but leaves a factor of 2 excess. Top-heavy IMFs are contradicted by direct IMF measurements. Exotic cosmological proposals like early dark energy or varying physical constants either conflict with other observations or create new problems as bad as the ones they solve. Nashwan Sabti and collaborators at Johns Hopkins tested whether modifying the matter power spectrum could help, and found that the changes needed to match JWST data would produce too many small galaxies, contradicting Hubble observations. Cosmological modifications alone, it appears, do not work. The solution almost certainly involves galaxy formation physics rather than fundamental changes to the cosmological model. Almost certainly, but not definitely. And that uncertainty, that stubbornly unresolved gap between what the universe is showing us and what our best model predicts, is itself the most important result of 3 years of JWST observations. Because, as Boylan-Kolchin noted, even after all corrections, even after removing AGN, accounting for burstiness, and applying every known systematic effect, a persistent factor of 2 excess in massive galaxies remains, and there are now individual anomalies that strain even the generous reading. a galaxy designated JDs-1050323 at Z equals 6.9 appears by its spectral energy distribution to contain a stellar population that is older than the universe was at the time we are observing it. Not by a small amount, by 4.7 sigma, a level of statistical significance that in particle physics would be considered a discovery. The universe, it seems, was in an extraordinary hurry, and 3.5 years after JWST opened its eyes and found the first impossible galaxies staring back. We still do not understand why, but to fully appreciate the depth of the problem and to understand what MOM-Z14's nitrogen is really telling us, we need to talk about what came before these galaxies existed, not as background, not as setup, as evidence, because the conditions that preceded MOM-Z14 make its existence even more bewildering than the numbers alone suggest. When the universe was 380,000 years old, something happened that defines everything that came after. The expanding, cooling plasma of protons and electrons that filled the cosmos finally cooled enough for hydrogen atoms to form. When electrons combined with protons into neutral atoms, the photons that had been endlessly scattering off free electrons were suddenly released. They streamed outward in every direction and have been traveling ever since, slowly redshifting from their original temperature of about 3000 Kelvin down to the 2.7 Kelvin cosmic microwave background that radio telescopes detect today. That moment, called recombination, marks the surface of last scattering, the oldest light we can see directly. Everything before it is hidden behind a wall of opaque plasma. After recombination, the universe went dark. There were no stars. There were no galaxies. There was nothing luminous at all, just an expanding, cooling fog of neutral hydrogen gas, roughly 75% hydrogen by mass and 25% helium, with trace amounts of lithium and nothing else. No carbon, no oxygen, no nitrogen, no silicon or iron or any of the elements that make up rocky planets, or chemistry, or people. The only photons were the fading remnants of the cosmic microwave background, stretching to longer and longer wavelengths, providing less and less energy. The temperature of the gas dropped from about 4000 Kelvin to roughly 60 Kelvin over the next 100 million years. This period is called the Cosmic Dark Ages, and it lasted from about 380,000 years to somewhere around 100 to 200 million years. After the Big Bang, during the Dark Ages, the universe was not completely featureless. Dark matter, which does not interact with light and therefore was not affected by recombination, had been quietly clumping under its own gravity since much earlier. Those invisible dark matter concentrations pulled ordinary gas inward, slowly, creating regions of slightly higher density. In those overdense regions, the gas began to cool and contract further, falling into the gravitational wells that dark matter had prepared for it. But the process was slow and it was fragile because the gas had no efficient way to cool itself. In the modern universe, gas cools by radiating energy through emission lines of heavy elements, carbon and oxygen in particular. In the Dark Ages, those elements did not exist. The only cooling mechanism was molecular hydrogen, H2, which is far less efficient. So the gas fell inward slowly, and the first structures to form were small. The first stars to emerge from this primordial gas are called population 3 stars, and they remain one of the great unseen objects in astrophysics. No population 3 star has ever been directly observed. Everything we know about them comes from numerical simulations and theoretical models, plus a few tantalizing indirect hints. The models predict that population 3 stars were enormous. Because the primordial gas had no heavy elements to cool it efficiently, the gas clouds that collapsed to form stars could not fragment as easily as modern gas clouds do. Modern star formation produces a range of masses, from tiny red dwarfs at 1/10 of a solar mass to rare massive stars at 50 or 100 solar masses. But in the metal-free primordial environment, the models predict that stars formed with characteristic masses of 30 to several hundred solar masses, possibly even exceeding 1,000 solar masses under the right conditions. These were monsters by any standard. A star of 300 solar masses would have been millions of times more luminous than the Sun, with a surface temperature exceeding 50,000 Kelvin, blazing blue-white in a universe that had been dark for 100 million years. They were also short-lived. A 300 solar mass star burns through its hydrogen fuel in roughly 2 million years. At the end of its life, depending on its exact mass, it either collapses directly into a black hole or detonates as a pair instability supernova, an explosion of such extraordinary violence that it completely destroys the star and scatters every atom of newly forged heavy elements into the surrounding gas. Those elements, the first carbon, the first oxygen, the first silicon and iron, then mixed into the surrounding pristine hydrogen and changed everything. The next generation of stars formed from gas that was now lightly enriched with heavy elements. Those elements allowed the gas to cool more efficiently, fragment into smaller clumps, and produce a more normal range of stellar masses. The transition from population 3 to the next generation, population 2, is one of the most consequential transitions in cosmic history. It is the moment the universe acquired the chemical complexity necessary for everything that came after, including, eventually, planets and chemistry and life. Now here is why this matters for MOM-Z14. The cosmic dark ages ended somewhere around Z equals 20 to 30, roughly 50 to 200 million years after the Big Bang. The first population 3 stars ignited, lived for a few million years, and died. Their supernovae enriched the gas with the first heavy elements. The second generation of stars formed, producing more heavy elements. Each cycle of star formation, enrichment, and recycling added to the chemical complexity of the gas. This is the process that builds up the abundances of elements like oxygen, carbon, and eventually nitrogen. MOM-Z14 existed at 280 million years. The Dark Ages ended, at the very earliest, around 100 million years. That gives you approximately 180 million years between the formation of the very first stars anywhere in the universe and the moment we are observing MOM-Z14 with its supersolar nitrogen and its 100 million solar masses of stars already assembled into a compact galaxy. 180 million years to go from literally nothing, from darkness and neutral hydrogen, to a galaxy that is 182 times brighter than our best physics predicted. To put this in human terms, imagine that civilizations work the way galaxies do in Lambda-CDM, you would expect a few campfires after a few generations, some primitive settlements after a few centuries, cities after a few thousand years. MOM-Z14 is the equivalent of finding a skyscraper, one generation after someone figured out how to light a fire. And the nitrogen makes it worse, because nitrogen is not a first-generation product. The first supernova produce oxygen and carbon. Nitrogen comes later, from the CNO processing of that carbon in intermediate mass stars, or in the hypothetical supermassive stars that Charbonneau proposed. Either pathway requires pre-existing heavy elements, which means at least one prior generation of star formation and enrichment. So the nitrogen in MOM-Z14 is not just telling us that stars existed before this galaxy. It is telling us that enough stars existed, and enough of them died and scattered their products, and enough of those products were recycled into new stars and processed through the CNO cycle to build up supersolar nitrogen abundances, all in less than 180 million years from a standing start of 0 heavy elements. The conventional pathways cannot do this. AGB stars with main sequence lifetimes of hundreds of millions to billions of years cannot contribute on this timescale. Wolf-Rayet stars from a second burst could briefly elevate nitrogen, but only if the timing is exquisitely precise, and only if the first burst happened early enough and was powerful enough. The supermassive star hypothesis bypasses the problem by proposing objects so massive that their cores run hot enough for the CNO cycle to operate at extreme efficiency, producing nitrogen directly from hydrogen burning at temperatures above 100 million Kelvin. These stars, if they existed, could produce the observed abundances in a single generation, but they would have to form through a mechanism, runaway collisions in extraordinarily dense stellar environments that has never been observed in the local universe. JWST may have found indirect evidence of population 3 stars. In GN-Z11's halo, a clump of ionized helium was detected with no accompanying heavier elements, consistent with roughly 600,000 solar masses of pristine primordial stars. That is a tantalizing hint, but not a confirmed detection. And MOM-Z14 itself, while clearly enriched with heavy elements, shows a chemical pattern that the paper argues is best explained by supermassive stars, not ordinary population 3 remnants. So the picture that is emerging is one where the very first stars, the ones that ended the Dark Ages, may have been even more exotic than the models predicted. Not just massive, but supermassive. Not just bright, but so luminous and energetic that they could forge the chemical complexity we see in MOM-Z14 within a timescale that would otherwise be physically impossible. And if that is true, then the early universe was not just in a hurry. It was running a fundamentally different kind of chemistry than anything we see around us today. This is the edge of what we know, the place where the data runs ahead of the theory, and the theory has not caught up. And the remarkable thing about this moment in astronomy is that the instrument capable of pushing further, of finding galaxies at even higher redshifts, of detecting the chemical signatures of even more exotic stellar populations, is already in orbit and already taking data. JWST is not done. The Mirage or Miracle survey is continuing. Deeper integrations are planned. More spectra are coming. Whatever the universe is trying to tell us, we are going to keep listening. There is a detail about MOM-Z14 that we have not yet fully reckoned with, and it changes the way you think about everything else JWST has found. It concerns what was happening in the space around the galaxy, not inside it. At a redshift of 14.44, the universe should have been almost entirely filled with neutral hydrogen. The epoch of Reionization, the period when ultraviolet radiation from the first stars and galaxies reionized that primordial hydrogen fog and made the universe transparent, was not supposed to be meaningfully underway at that point. Reionization started as expanding bubbles of ionized gas around individual galaxies and clusters, bubbles that grew and overlapped over hundreds of millions of years. The process began perhaps as early as Z equals 16, roughly 250 million years after the Big Bang. But it was not mostly complete until Z equals 9 or 10, about 500 million years in. It was fully finished by Z equals 5 or 6, about 1.1 billion years, as confirmed by Sarah Bosman's team at the Max Planck Institute in 2022. The intergalactic medium went from a cold neutral fog at maybe 10 to 1,000 Kelvin to a hot ionized plasma at roughly 20,000 Kelvin over that extended period. So at Z equals 14.44, at 280 million years, models predict the neutral hydrogen fraction should be close to 100%. The fog should be total. The universe at that epoch should be opaque to ultraviolet light in almost every direction. But MOM-Z14's immediate surroundings appear to be partially ionized. The spectrum shows evidence that a bubble of ionized gas has formed around the galaxy, a region where the neutral hydrogen has been cleared away by the galaxy's own ultraviolet radiation. This is not impossible in principle. A sufficiently luminous galaxy can ionize its local environment. Stars produce ultraviolet photons with enough energy to strip electrons from hydrogen atoms. And if enough of those photons escape the galaxy and reach the surrounding intergalactic medium, they create an expanding sphere of ionized gas, a bubble in the fog. Individual bubbles around individual galaxies and clusters are thought to be the building blocks of reionization, growing and eventually overlapping until the entire intergalactic medium is ionized. But the size of the ionized region, implied by the data around MOM-Z14, suggests that this galaxy, and possibly other galaxies nearby that we have not yet detected, have been pumping out UV photons for long enough and at a high enough rate to carve a significant bubble in the otherwise completely neutral intergalactic medium. At a time when reionization was barely getting started. This matters because it connects the impossible galaxies problem to a separate, long-standing puzzle in cosmology, the reionization budget problem. For over a decade, astronomers have been trying to figure out whether the galaxies we can see at high redshift produce enough UV photons to account for the entire reionization of the universe. It is a bookkeeping exercise with enormous implications. You count the galaxies. You estimate their UV output. You calculate the total number of ionizing photons they collectively produce. And you compare that to the number of hydrogen atoms in the intergalactic medium that need to be ionized. The answer, using pre-JWST galaxy counts, was always borderline. There seemed to be barely enough galaxies, or possibly not quite enough, to get the job done. A popular hypothesis was that the missing photons came from very faint, low-luminosity galaxies below the detection threshold of Hubble. galaxies so small and dim that even Hubble's deep fields could not see them, but that collectively produced enough UV light to tip the balance. But JWST is now finding that the early universe had far more luminous galaxies than expected. If bright galaxies at Z equals 10 to 15 are 100 to 200 times more numerous than predicted, the Reionization budget is not short at all. It is potentially oversubscribed. There might be too many UV photons, which would drive Reionization earlier and faster than current models suggest. MOM-Z14, sitting inside its own ionized bubble at Z equals 14.44, could be the first direct evidence of this accelerated reionization. The universe is not just building galaxies faster than expected. Those galaxies may be transforming the universe around them faster than expected too, clearing the fog earlier, heating the intergalactic medium sooner, and reaching the kind of cosmic transparency that models said would take much longer to achieve. And this raises a question that has been hovering over the field since 2022, but is only now coming into sharp focus. If the galaxies are too numerous, too bright, too chemically mature, and if they are also reionizing the universe faster than predicted, then where do all the models go wrong? Is it one thing, one parameter, one process that we have miscalibrated? Or is the problem distributed across a dozen different assumptions that all happen to be slightly off in the same direction? Because the honest answer, as of early 2026, is that nobody knows. And the attempts to find out have fractured the theoretical community in a way that is itself part of the story. We covered the three main theoretical responses earlier: bursty star formation, AGN contamination, and modified initial mass functions. But we did not explore how they interact with each other, or what it means that each one explains part of the picture while leaving the rest untouched. And this is where the real scientific tension lives. Not in any single result, but in the aggregate. Start with the bursty star formation camp. Their argument is the most conservative and, in some ways, the most elegant. Guo Chao's son and the fire simulation team at Northwestern showed that if you model star formation with realistic supernova feedback, you get natural cycles of boom and bust. A region of gas collapses, forms a burst of massive stars, and for a few million years, the galaxy blazes at maximum luminosity. Then those massive stars explode, heating and dispersing the gas, suppressing further star formation for tens of millions of years. The galaxy fades, then the gas cools, falls back in, and the cycle repeats. At any given moment, some fraction of early galaxies are caught at their brightest, and that bright fraction is much larger than a smooth star formation model would predict. The beauty of this explanation is that the total stellar mass does not need to be higher than Lambda-CDM predicts. The galaxies are not heavier, they are just flashier. You are seeing them during their brief moments of maximum output. This genuinely works for the UV luminosity function. The fire predictions, made before JWST launched, match the observed luminosity distribution at Z greater than 10 remarkably well. That is not nothing. A pre-launch prediction matching post-launch observations is exactly how science is supposed to work, and it lends real credibility to the burstiness explanation. But, and this is the critical transition, burstiness explains brightness. It does not explain mass. When you look at the actual stellar masses of early galaxies, not their luminosity, but the amount of matter locked up in stars, as inferred from spectral fitting, you still find objects that are too massive. Even accounting for the fact that brightness fluctuates, the total mass accumulation requires more stars to have formed in total than feedback-regulated models allow. And burstiness certainly does not explain the nitrogen anomaly, because nitrogen enrichment depends on the total integrated history of star formation, not on whether you happen to catch a galaxy during a burst. The nitrogen is there whether the galaxy is currently bright or currently dim. Then there is the AGN camp, led most visibly by Catherine Chorosky and Stephen Finkelstein. Their contribution was crucial because it addressed a genuine systematic error in the early data. Many of the so-called impossibly massive galaxies from JWST's first year of data turned out to host active galactic nuclei, accreting supermassive black holes whose radiation inflated the apparent brightness and mass of the host galaxy. When you carefully decompose the light into a stellar component and an AGN component, many of the most extreme mass estimates drop dramatically. The galaxies that were supposedly 10 billion solar masses at Z equals 7 turn out to be, in some cases, a few hundred million solar masses with a bright AGN on top. Finkelstein's summary of this work was direct and quotable. There is no crisis in terms of the standard model of cosmology. And within the narrow frame of the mass function, he had a point. Strip out the AGN contaminated objects and the remaining galaxy population, while still on the high side, falls much closer to Lambda-CDM predictions. But here is the thing Finkelstein's framing does not address. First, even after AGN removal, there are still roughly twice as many massive galaxies as predicted. A factor of 2 is a real discrepancy, and it has resisted every attempt to explain it away. Second, and more fundamentally, the existence of those active galactic nuclei is itself a problem. GNZ11's 2 million solar mass black hole at 430 million years after the Big Bang is a challenge for black hole formation models, quite independent of what it does to galaxy mass estimates. Growing a black hole that large, that fast, requires either extremely efficient accretion at or above the theoretical Eddington limit for extended periods, or the existence of massive seed black holes, perhaps from the direct collapse of primordial gas clouds that have never been observed. Removing AGN from the galaxy mass problem does not make the AGN problem go away. It just moves the unexplained phenomenon from one column to another. And the little red dots, these compact, red, photometrically peculiar objects that JWST has been finding in large numbers, represent an entire population of objects the pre-JWST theory did not predict. Some of them are clearly AGN dominated. Others show a mix of stellar and nuclear emission. Their nature is still actively debated, with papers appearing monthly proposing different interpretations. What is clear is that the early universe produced a substantial population of compact objects with supermassive black holes that do not fit neatly into any pre-existing category. Whether they end up being classified as galaxies, quasars, or something entirely new, they represent a mode of early cosmic assembly that our models did not anticipate. The third camp, the IMF modifiers, had the most intuitive solution and the most devastating empirical rebuttal. If early galaxies produced proportionally more massive, luminous stars than local galaxies do, then you could explain the brightness without invoking more total mass. Ann Hutter's 2025 paper showed that a top-heavy IMF could boost UV luminosity by up to 2.6 magnitudes. That is a lot. It would go a long way toward explaining why early galaxies appear brighter than predicted. But Chloe Cheng's JWST MFERNO results from January 2026 measured the actual IMF in evolved descendants of the early impossible galaxies and found the opposite, not top-heavy, bottom-heavy. These galaxies have an excess of low-mass stars relative to the standard IMF. That means their total stellar mass is higher than you would infer using a standard IMF assumption by a factor of 3 to 4. So instead of solving the mass problem, the IMF measurement makes it worse. The early galaxies are not just as massive as they appeared. They may be several times more massive. Now, you could argue that the early galaxies themselves might have had a different IMF than their descendants. The IMF might evolve with redshift. The early universe might have produced top-heavy IMFs that subsequently transitioned to bottom-heavy ones as conditions changed. This is not impossible, but it is also not predicted by any existing model, and it introduces an additional free parameter that makes the whole theoretical framework feel increasingly ad hoc. You are no longer explaining the observations from first principles. You are fitting them after the fact by adjusting knobs. And this is where Boylan-Kolchin's nuanced assessment becomes particularly important. Most people would put their money on the astrophysical explanation right now, he said, meaning some combination of burstiness, AGN contamination, IMF effects, and other galaxy physics adjustments within the Lambda-CDM framework. He is probably right. The most likely outcome is that we will eventually identify a set of astrophysical processes that, taken together, account for most of what JWST is seeing without requiring any changes to fundamental cosmology. Lambda-CDM is an incredibly well-tested model. It would take extraordinary evidence to overturn it, and we are not there yet. But Boylan-Kolchin also noted the persistent factor of 2 excess in massive galaxies after all corrections, and the 4.7 sigma anomaly of JD's 1050323, which appears to contain stars older than the universe at its observed epoch, and the nitrogen enrichment that no conventional model can fully account for, and the protocluster with hot gas 2 billion years before models allow. Taken individually, each of these might be a statistical fluctuation, a measurement error, or an unexplored corner of conventional physics. Taken collectively, they paint a picture of an early universe that is systematically ahead of schedule in ways that consistently push in the same direction. At the margins, more exotic proposals exist. Xuejian Shen and collaborators, in a 2024 paper in the monthly notices of the Royal Astronomical Society, proposed that early dark energy, a hypothetical phase of dark energy that was active in the early universe and then faded away, could simultaneously help explain the Hubble tension and the UV bright galaxy excess. Early dark energy was originally proposed to address a completely different problem: the disagreement between local and cosmic microwave background measurements of the Hubble constant. If it turns out to also improve the fit to JWST's early galaxy data, that would be a compelling convergence of evidence from independent observations. But early dark energy is speculative. not yet confirmed by any single observation, and it comes with its own set of theoretical challenges. Further out on the fringe, Rajendra Gupta of the University of Ottawa proposed in 2023 that the universe might be 26.7 billion years old rather than 13.8 billion, based on a model with varying physical constants. If true, the impossible early galaxies would have had twice as much time to form and would not be impossible at all. But this proposal requires modifying fundamental physics in ways that conflict with a vast body of independent evidence, and it has not gained traction in the mainstream community. The most careful theoretical work by Nashwan Sabti and colleagues at Johns Hopkins tested whether modifications to the matter-power spectrum, the statistical description of how matter clumps on different scales in the early universe, could help. They found that the changes needed to produce more bright galaxies at high redshift would simultaneously produce too many smaller galaxies, in conflict with Hubble observations at lower redshifts. This is a critical result because it closes off one of the cleanest theoretical escape routes. You cannot just turn up the amplitude of matter fluctuations to get more early galaxies without creating too many at later times. The constraint from Hubble data pins the other end. Their conclusion was stark. Cosmological modifications alone do not work. The solution lies in galaxy formation physics. But as we have seen, the galaxy formation physics explanations are each incomplete in different ways, and nobody has yet produced a single coherent model that accounts for brightness, number density, chemical maturity, structural diversity, and large-scale structure formation timescales all at once. The pieces of the puzzle are on the table. Nobody has assembled them. That is the state of the field as of February 2026. An enormous amount has been learned. An enormous amount remains unexplained. And the most important thing to understand about this moment is that it is not a crisis of confusion. It is a crisis of abundance. The data is too rich and too surprising for the existing theoretical tools to process. But those tools are being sharpened, and the data keeps flowing. And somewhere in the space between what we see and what we understand, the next breakthrough is forming. But there is one more dimension to this story that we have not properly explored, and it may turn out to be the most profound one. It concerns the two galaxies at Z greater than 14 that JWST has confirmed, and what they tell us when you compare them side by side. MOM-Z14 and JADES-GS-Z 14-0 both existed roughly 280 to 290 million years after the Big Bang. They are separated by only about 10 million years in cosmic time, close enough that they are essentially contemporaries. They are the two most distant spectroscopically confirmed galaxies in the observable universe, and they are nothing alike. JADES-GS-Z 14-0 is extended over 1,600 light-years across, maybe larger. It has several hundred million solar masses in stars. It is bright at UV wavelengths, and ALMA detected oxygen in it, but its nitrogen emission is weak. Its UV slope suggests some dust and a relatively mature stellar population. It looks, for all the world, like a young galaxy that has been forming stars at a steady or gradually increasing rate for tens of millions of years. MOM-Z14 is compact, roughly 240 light-years across, 400 times smaller than the Milky Way, about 100 million solar masses, blazing bright in the UV, with an extremely steep UV slope of beta equals -2.5, indicating virtually no dust and an extremely young stellar population. It shows a rising star formation history with a roughly 10-fold increase in star formation rate over the last 5 million years. It was caught mid-starburst, and it has that extraordinary nitrogen, the super-solar N/C ratio, the N4 emission line that connects it to GN-Z11 and to the ancient globular clusters of our own galaxy. These two objects are almost exact contemporaries in cosmic time, and they represent radically different modes of galaxy formation. One is big, extended, and chemically moderate. The other is tiny, dense, and chemically extreme. The universe, just 280 million years after the Big Bang, was already producing dramatically diverse galaxies through what appear to be fundamentally different physical processes. This diversity is itself a problem for models. Lambda-CDM's hierarchical assembly predicts a relatively uniform population of small protogalactic fragments at these early times. You might expect some scatter in mass and brightness, but the qualitative differences between MOM-Z14 and JWST-Z14-0, the compact nitrogen-rich versus the extended oxygen-rich, suggest different formation pathways operating simultaneously. The size chemistry bimodality that Naidu's team identified is not just a curious pattern, it is evidence that the early universe had multiple channels for building galaxies, and we do not yet understand what determines which channel a given region of gas and dark matter follows. The compact nitrogen-rich channel might be producing something like proto-globular clusters, dense stellar systems where runaway collisions create supermassive stars that enrich the gas with nitrogen through extreme CNO processing. The extended oxygen-rich channel might represent more conventional hierarchical assembly, where gas falls into a dark matter halo over a wider area and forms stars more gradually, enriching the interstellar medium primarily through ordinary core collapse supernovae. If both channels operate in the early universe, the chemical diversity JWST is finding would be a natural consequence of the different physical conditions in different environments. Dense regions produce compact, nitrogen-rich objects. More diffuse regions produce extended, oxygen-moderate objects. Both are happening simultaneously, just 280 million years into cosmic history. And here is where the connection to globular clusters becomes not just intriguing, but potentially foundational. The Milky Way contains about 150 globular clusters. They are the oldest structures in our galaxy, with ages of 12 to 13 billion years, meaning they formed in the first billion years after the Big Bang. They have long been mysterious in their own right, because their stars show abundance patterns that do not match anything produced by normal stellar evolution. Multiple stellar populations within the same cluster show different helium, nitrogen, and sodium abundances, a pattern that has been attributed to pollution from a first generation of extremely massive stars, possibly supermassive stars exceeding 1,000 solar masses that enriched the gas before the second generation formed from it. For decades, this was a theoretical inference. We knew the abundance patterns existed in nearby globular clusters. We knew they required an exotic enrichment source. We hypothesized supermassive stars, but we had never seen the actual formation site. We had never witnessed the process in action, MOM-Z14 might be that site. Its chemical fingerprint, the supersolar nitrogen, the compact size, the dense stellar environment, matches what the globular cluster models require for the first-generation enrichment source. If the interpretation holds, we are not just seeing the most distant galaxy. We are seeing the birthplace of objects that still orbit our own galaxy today. The globular clusters that you can photograph through a backyard telescope on a clear night. Those ancient swarms of stars that have been circling the Milky Way for 13 billion years may have been born in conditions like the ones we see in MOM-Z14. Naidu's paper makes this connection explicit. We may be directly witnessing the formation of such stars in dense clusters, connecting galaxy evolution across the entire sweep of cosmic time. That sentence, buried in a technical astronomy paper, carries an almost poetic weight. Across the entire sweep of cosmic time, from 280 million years after the Big Bang to today, from a faint red smudge in the infrared to the ancient star clusters visible in our own sky. One continuous thread, and it is fitting, perhaps, that the person who drew that thread is himself a poet. Naidu is not just an astronomer. He is a published poet whose work has appeared in the Quarterly Literary Review Singapore and was long-listed for the University of Canberra Vice-Chancellor's International Poetry Prize. There is something in the way he writes his papers, in the way he names his surveys and frames his discoveries, that reflects a mind comfortable with both precision and meaning. The survey is called Mirage or Miracle. The paper is titled A Cosmic Miracle. The galaxy's name, MOM-Z14, encodes both the question and the answer. Was it a mirage or a miracle? It was a miracle, and the miracle connects to the oldest structures in our own cosmic backyard. On his website, Naidu provides a pronunciation guide for his name. Rohan, he writes, Ro like the Greek letter, plus Hon like honey. Naidu. Nye like Bill Nye, plus Do like Scooby-Doo. There is a playfulness in that, a willingness to make the personal accessible. That runs through his scientific work too. This is a man who dropped out of engineering school in Hyderabad, flew to Singapore on his first ever plane ticket, discovered astronomy in the Chilean Andes, earned his PhD from Harvard under Charlie Conroy, became a NASA Hubble Fellow and Pappalardo Fellow at MIT's Kavli Institute, and at 30 years old, led the team that confirmed the most distant galaxy in human history. He has over 6,500 citations on Google Scholar. He is moving to the University of Hawaii as a tenure-track assistant professor in the summer of 2026. And somewhere between the blazers and the spectral lines, he writes poetry. The arc of that career mirrors the arc of the discoveries in a way that is almost too neat. A young person from an unexpected background, taking an improbable path, ending up at the frontier of human knowledge and finding something nobody predicted. That is, in miniature, what the early universe did. It took an improbable path. It built things nobody predicted. And it did so with a speed and a creativity that defied every careful calculation. Now, understanding how we actually extract information from a smudge of photons that has been traveling for 13.53 billion years requires understanding the instruments that make it possible. And this is not a detour from the story. It is central to it, because the entire saga of impossible galaxies is, at its core, a story about the difference between what you think you see and what you actually confirm. CEERS-93316 looked like a galaxy at Z equals 16.7 until the spectrograph proved it was at Z equals 4.9. The Mirage or Miracle survey exists because the difference between Mirage and Miracle can only be resolved spectroscopically. The instruments are not just tools. They are the arbiters of reality. JWST carries two instruments that matter most for this story. The first is NIRCam, the near-infrared camera, which was built under the leadership of Marcia Reek at the University of Arizona. NIRCam operates from 0.6 to 5.0 micrometers across two optical modules containing a total of 40 million pixels. It takes images, high-resolution, exquisitely sensitive images in the near-infrared, the wavelength range where the light from the most distant galaxies has been redshifted by cosmic expansion. NIRCam is the discovery engine. It surveys large areas of sky through multiple filters and identifies galaxy candidates through the Lyman break dropout technique, looking for objects that appear in some filters but vanish in others. For MOM-Z14, NIRCam imaged the survey field in 10 filters from F090W at the short end to F444W at the long end. The galaxy was invisible in the three shortest wavelength filters, F090W, F115W, and F150W, but clearly detected from F200W onward. That pattern of absence and appearance is the signature of a Lyman break at approximately Z equals 14. NIRCam saw it, but NIRCam could not prove it. That is where NR-spec comes in. NR-spec, the near-infrared spectrograph, operates over a similar wavelength range, 0.6 to 5.3 micrometers, but instead of taking images, it disperses the light into a full spectrum. Every wavelength is separated and recorded individually. This is how you identify specific emission and absorption lines, the chemical fingerprints of atoms and ions at precise wavelengths. NIR-spec's most remarkable engineering feature is its micro-shutter assembly, a grid of approximately 250,000 individually addressable shutters, each one smaller than a human hair, that can be opened or closed to select which objects on the sky have their light sent through the spectrograph. This allows observation of roughly 100 objects simultaneously, a massive efficiency gain over previous spectrographs that could only observe one object at a time. For MOM-Z14, NIR-spec in its prism mode confirmed Z equals 14.44 through two independent lines of evidence. First, the Lyman alpha break, the sharp cutoff in the spectrum where neutral hydrogen absorption eats everything blueward of the break. Second, those 5 rest frame ultraviolet emission lines, including the N4 nitrogen line, detected at their precisely predicted wavelengths for a galaxy at that redshift. The spectroscopic redshift has a precision of plus or minus 0.02 compared to photometric redshift uncertainties of plus or minus 0.5 or more. That is a factor of 25 improvement in precision, and it is the difference between a candidate and a confirmation. This distinction between photometry and spectroscopy, between candidate and confirmation, has been the methodological spine of the entire 3-year story. The initial flood of candidates in July 2022 was photometric. The CEERS 93,316 debunking was spectroscopic. The JADES conformations at Z greater than 10 were spectroscopic. The nitrogen detections in GNZ 11 and MOMZ 14 were spectroscopic. Every time the field has taken a major step forward, it has been because a spectrograph separated the light into its component wavelengths and showed what was actually there. Photometry is the scout, spectroscopy is the judge, and the Lyman break technique itself, the foundational method underlying all of this, is worth appreciating for a moment because it is a beautiful piece of physics turned into an observational tool. Neutral hydrogen is opaque to ultraviolet light at wavelengths shorter than 121.6 nanometers. Every photon with enough energy to excite the Lyman alpha transition in hydrogen gets absorbed. In the local universe, this absorption happens in the far ultraviolet, well below the range of ground-based telescopes. But at high redshift, the expansion of the universe stretches everything. At Z equals 14, Lyman alpha has been redshifted from 121.6 nanometers all the way out to 1.8 micrometers, solidly in the near-infrared. The break, the sharp edge where the spectrum drops to zero, has moved from ultraviolet wavelengths that we cannot observe from Earth to infrared wavelengths that are perfectly suited to JWST's cryogenic mirrors and detectors. This is why JWST had to be cold. Its mirrors and instruments operate at -233 degrees Celsius or below, shielded from the sun by a 5-layer sun shield the size of a tennis court. If the telescope itself were warm, its own thermal infrared radiation would drown out the faint signals from distant galaxies. Observing the Lyman break of a Z equals 14 galaxy in the near-infrared is like trying to hear someone whispering in a room full of loud machinery. You need to silence the machinery. JWST silences it by being colder than almost anything in the solar system, orbiting 1.5 million kilometers from Earth at the second Lagrange point, forever in the shadow of its own sun shield. The engineering required to put a 6.5-meter segmented mirror, an array of infrared detectors, and a micro-shutter assembly with 250,000 shutters into stable cryogenic operation. 1.5 million kilometers from the nearest repair shop is itself one of the great technological achievements of human civilization. And it works. It works so well that it has found things we did not know were there. The technique was pioneered by Charles Steidl and Douglas Hamilton in 1993, when they realized that the Lyman break could be used as a natural redshift indicator for distant galaxies observed through broadband filters. Steidl's Lyman break galaxies at Z equals 3 were, at the time, the most distant galaxies known. 3 decades later, the same technique, applied with instruments that Steidl could not have imagined, is finding galaxies at Z equals 14. The physics has not changed. The light still breaks at the same wavelength, but the instruments have changed so dramatically that we are now seeing 400 million years deeper into the past than Steidl's first Lyman break galaxies, and finding things that break the models those galaxies helped to build. There is a misconception worth addressing here, because it circulates widely in popular accounts and even in some media coverage of these discoveries. The misconception is that JWST has somehow seen back to the Big Bang, that we are looking at the very first moments of the universe. We are not. The earliest galaxies JWST has found exist at roughly 280 to 350 million years after the Big Bang. That is extraordinarily early, but it is not the beginning. The cosmic microwave background, released at 380,000 years, is much older, and it is visible to microwave telescopes, not infrared ones, between 380,000 years and roughly 100 million years, the cosmic dark ages. There was nothing luminous to see. JWST cannot see into the dark ages because there was nothing emitting infrared light during that period. What JWST sees is the epoch immediately after the dark ages, the period called cosmic dawn, when the first stars and galaxies turned on. MOM-Z, 14 at Z equals 14.44, exists about 180 million years after the first possible stars could have formed. It is very early. It is not the beginning, and the gap between the beginning and what JWST can see is itself filled with physics that we have never directly observed. The formation of the first population 3 stars, the first supernovae, the first chemical enrichment of pristine gas. Everything JWST finds at Z equals 10 to 15 is already the product of at least some prior star formation. We are seeing the output of the process, not the process itself. Correcting this misconception matters because it sharpens the puzzle. MOM-Z14 is not the first galaxy. It cannot be. It already has heavy elements. It already has nitrogen. It already has 100 million solar masses of stars. The first galaxies, whatever they were, existed earlier and were presumably smaller and simpler. MOM-Z14 is already several steps into a process that must have started before it. And the fact that those several steps produce something this luminous, this massive, and this chemically complex in less than 180 million years is what makes the whole thing so bewildering. And speaking of the process, it is worth acknowledging just how much of this story has been shaped by decisions made years or decades before the data arrived. The surveys that produced these discoveries were not improvised. They were carefully designed campaigns, each with specific scientific goals, allocated through fiercely competitive peer review processes, and executed by teams that had been planning and preparing for years. Consider the scope of the effort. JWST, observing time, is among the most precious resources in all of science. The telescope can only look at one thing at a time. Every hour spent on one survey is an hour not spent on another. The cycle one-time allocation process, which decided what JWST would observe in its first year, received proposals requesting roughly 10 times more time than was available. The programs that won had to survive review by expert panels who evaluated scientific merit, feasibility, and expected impact. The surveys that produced the impossible galaxies were, in every case, programs that the astronomical community judged to be among the most important things the most expensive telescope ever built could do. JDS, the survey that confirmed the first batch of Z greater than 10 galaxies and later produced JDS GSZ 14-0, is the largest Cycle 1 program on JWST, roughly 770 to 800 hours of observing time. To put that in context, JWST operates about 24 hours a day and observes for roughly 250 days per year between calibrations and other overhead. JDS consumed nearly 15% of the entire first year of observations. It was co-led by Daniel Eisenstein at Harvard, one of the architects of the Baryon Oscillation Spectroscopic Survey who knows large survey design at a level few others match, and Andrew Bunker at Oxford, whose 2 decades on the NIR Spec instrument science team gave him an intimate understanding of what the spectrograph could and could not do. JDs targeted the Goods South and Goods North fields deliberately because these are among the most studied patches of sky in all of astronomy. Hubble had already spent weeks staring at them. Chandra had built up the deepest X-ray exposures ever taken in the same fields. Spitzer had infrared coverage. By choosing these particular patches of sky, JDs ensured that any JWST discovery could immediately be cross-referenced with data from every other major observatory. This is why Akos Bogdan was able to find the X-ray emission from JDES YD1. The protocluster happened to sit in a field where Chandra had already accumulated the deepest X-ray observation in history. Without that overlap, without that deliberate decision to observe where Chandra had already observed, the hot gas would never have been detected. CEERS, led by Stephen Finkelstein, was designed as an early release science program, one of the first to deliver data after JWST's commissioning. 77 hours of observing time covering roughly 100 square arc minutes of the extended Groth strip. SEERS was always intended to move fast, to demonstrate JWST's capabilities quickly and get data into the hands of the community. It produced both Maisie's Galaxy and the cautionary tale of CEERS 93316 within weeks of the first observations. Finkelstein's willingness to publish both the successes and the failures, to celebrate the confirmation of Maisie's Galaxy, and accept the debunking of CEERS 93316 with equal scientific equanimity, set a tone for the field that mattered. This was not going to be a story of hype and retraction. It was going to be a story of careful, iterative discovery, where every photometric candidate had to earn its redshift through spectroscopic confirmation, glass, the Grism lens, amplified survey from space led by Tommaso Tro at UCLA, was another early release science program, and the one that produced the very first ultra-high redshift candidates in July 2022. GLASS used the gravitational lensing effect of galaxy cluster Abell 2744 to magnify the light from background galaxies, effectively turning the cluster into a cosmic telescope layered on top of JWST itself. Gravitational lensing bends and amplifies light from distant sources that happen to lie behind a massive foreground object. The result is that galaxies too faint to detect with JWST alone become visible when their light is magnified by a factor of 2 or 5 or 10 by an intervening galaxy cluster, GLASS Z13, later redesignated GLASS Z12 or GHZ2, and eventually confirmed at ZZ equals 12.34 by both ALMA and NIR Spec, was one of the very first objects to signal that something unexpected was happening in the early universe. The fact that it was found within days of the first data release, independently by teams on 2 continents, speaks to how conspicuously bright these objects were. They did not require deep searching. They practically announced themselves. Uncover, co-led by Rachel Bezenson at the University of Pittsburgh and Ivo Laber, took the gravitational lensing approach even further, also targeting galaxy cluster Abell 2744. Uncover combined ultra-deep JWST imaging with spectroscopic follow-up to find some of the faintest and most magnified high redshift galaxies. The Uncover program has been particularly important for studying the little red dots, those compact AGN-dominated objects that complicate the mass estimates of early galaxies. Much of what we know about the prevalence and properties of these enigmatic objects comes from Uncover data. And then there was the Mirage or Miracle survey itself, designed by Naidu and Uesch specifically to resolve the Mirage versus Miracle question. 350 square arc-minutes across the cosmos and UDS fields, with a spectroscopic follow-up strategy built into the survey design from the start. MOM was not an imaging survey that happened to get spectroscopy later. It was a spectroscopic survey that used imaging to select targets. The entire point was to take the ambiguity out of high redshift galaxy identification. Mirage or Miracle? Yes or no? And when the answer came back Miracle for MOM-Z14, it came with 5 emission lines and a redshift precision of plus or minus 0.02. There was no ambiguity left. The deliberateness of these survey designs matters because it undercuts a narrative that sometimes appears in popular coverage. The narrative that JWST's discoveries were accidents, lucky finds, serendipitous encounters with objects nobody was looking for. That narrative is mostly wrong. JWST found impossible galaxies because extremely talented people designed extremely sophisticated surveys to look for exactly those objects in exactly those patches of sky with exactly the right instruments. The universe surprised them with the results, but the search itself was anything but random. There is something else worth saying about these surveys, and it concerns what comes next. JWST is not done. The telescope has a projected operational lifetime of at least 20 years, potentially longer, limited primarily by its fuel supply for orbital station keeping. As of early 2026, it has been operating for about 3.5 years. It is, by any measure, still in the early phase of its scientific life. Cycle 3 observations are underway. Cycle 4 proposals are being evaluated. Deeper integrations on known high redshift fields will push the sensitivity limit further, potentially revealing galaxies at Z equals 15, 16, or beyond. The MOM survey itself is continuing, with additional spectroscopic targets being observed, and entirely new survey strategies are being developed based on what the first 3 years have taught us. This is critical because the impossible galaxies problem is not static. It is evolving with every new observation. The factor of 182 excess in number density at Z equals 14 to 15 was measured from a relatively small survey area. As more area is covered and more spectra are taken, that number will be refined. It might come down. It might go up. The nitrogen anomaly has been confirmed in 2 galaxies at Z greater than 10. If it appears in 5 more or 10 more, the supermassive star hypothesis moves from speculative to compelling. If it turns out to be absent in most Z greater than 10 galaxies and confined to a rare subset, the interpretation changes. More data will decide. And JWST is not the only instrument bearing on this question. ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, has already detected oxygen in JADES-GS-C14-0. Its ability to observe far infrared emission lines that are redshifted into the millimeter band makes it the perfect complement to JWST's near-infrared capabilities. The European Extremely Large Telescope, currently under construction in Chile with a 39-meter primary mirror, will provide ground-based spectroscopy at resolutions JWST cannot match, potentially resolving the internal structures of high redshift galaxies and measuring their dynamics. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA in the late 2020s, will survey vastly larger areas of sky than JWST can, providing the statistical power to measure number densities and luminosity functions with much smaller uncertainties. The question of whether the early universe is genuinely overproducing galaxies, or whether current surveys are affected by cosmic variance, statistical fluctuations due to looking at small patches of sky, will be definitively answered by Roman's wide field surveys. The tools are converging, the data is accumulating, and the theoretical community is responding with an intensity that matches the observational pace. Dozens of papers appear every month proposing new models, testing existing ones against updated data, and running simulations with increasingly realistic physics. The field is in one of those rare periods where observation is genuinely ahead of theory, where the data is telling us things we do not yet have the conceptual framework to fully understand. Those periods, historically, are when the biggest breakthroughs happen. Not when theory predicts and observation confirms, but when observation surprises and theory scrambles to catch up. There is another human thread in this story that deserves its full arc, and it belongs to Stephen Finkelstein. His role in this saga has been particularly interesting because he has consistently been the voice arguing that the crisis is overstated, that AGN contamination explains most of the mass excess, and that Lambda-CDM is fundamentally fine. There is no crisis in terms of the standard model of cosmology, he said in 2024, and he meant it. Finkelstein is not a contrarian or a denier. He is a careful observational astronomer who believes the data, when properly analyzed, does not require new physics. His position is that the initial shock of JWST's early results was partly driven by improper accounting for AGN light, and that as the field has matured and the analysis has become more sophisticated, the tension has decreased, and he has evidence for this position. The little red dots are real. A GN contamination was real. Many early mass estimates were too high. The factor of 2 excess that remains after corrections is notable but not catastrophic. From within Finkelstein's framework, the universe is unusual but not impossible, and the standard model holds. But what makes his position so interesting is the context. This is the same Stephen Finkelstein who named Maisie's galaxy on his daughter's birthday. The same Finkelstein who ran one of JWST's first major surveys and published both its triumphs and its embarrassments with equal transparency. The same Finkelstein who watched CEEERS 93,316 go from the most distant galaxy candidate in history to a perfectly ordinary Z equals 4.9 object, and said publicly that this was probably always the most likely outcome. His entire approach to this field has been characterized by a kind of grounded pragmatism that serves as a counterweight to the more dramatic interpretations. Whether Finkelstein turns out to be right or wrong about the severity of the crisis matters less than the fact that his perspective is part of the scientific process working as it should. You need people pushing back. You need people insisting that extraordinary claims require extraordinary evidence. You need someone to say, "Hold on, have we accounted for this systematic effect before we throw out the standard model?" That is not obstruction, that is rigor. And the tension between Finkelstein's cautious interpretation and Boylan-Kolchin's more concerned one, between no crisis and Precambrian rabbit, is the productive tension that drives science toward better answers. What is remarkable is that both positions coexist in the same department. Finkelstein and Boylan-Kolchin are both at the University of Texas at Austin. They work in the same building, they attend the same seminars, and they disagree, publicly and substantively, about whether JWST has revealed a fundamental problem with our understanding of the universe. This is not dysfunction. This is what healthy science looks like. Two smart people, armed with the same data, reaching different conclusions because they weight different pieces of evidence differently. Finkelstein looks at the AGN-corrected mass function and sees a manageable discrepancy. Boylan-Kolchin looks at the nitrogen anomaly and the proto-cluster timescales and the 4.7 sigma age anomaly in JDES 10503323 and sees something that might not be manageable at all. The universe will eventually tell us which one is closer to the truth. In the meantime, the argument makes both of their positions sharper. Let us now try to take the full measure of what has been discovered and what it means, because the sheer scope of numbers involved in this story can numb you if you are not careful. Redshift 14.44, 280 million years, 13.53 billion light-years of travel, 33.8 billion light-years of current distance, 100 million solar masses. These are figures that the human brain did not evolve to process. We need to translate them. If the entire 13.8 billion year history of the universe were a single calendar year, beginning on January 1st, the cosmic microwave background would have been released about 12 minutes past midnight on New Year's Day. The cosmic dark ages would have lasted until roughly January 5th. MOM-Z14 was already shining by January 7th. 1 week into the year, the Sun and Earth would not form until September. Dinosaurs would appear around December 25th, Christmas Day. All of recorded human history, every civilization, every war, every building ever constructed, every person who ever lived, occupies less than half a second before midnight on December 31st. MOM-Z14 existed in the first week, and it already had nitrogen. If you compress the universe's age into a single 24-hour day starting at midnight, MOM-Z14 existed at 12:29 in the morning. Half an hour in, the sun would not ignite until 4:30 in the afternoon. Humans would appear roughly 1/10 of a second before the next midnight. If cosmic history were a 100-yard football field, MOM-Z14 would sit at the 2-yard line, effectively at the goal line. And yet it contained 100 million stars, organized into a compact galaxy, already chemically enriched beyond what any model predicted. If the age of the universe were the distance from New York to Los Angeles, about 2,800 miles, then 280 million years would correspond to roughly 57 miles. You would barely be out of New Jersey. And in that distance, the universe had already built something that, based on our best understanding, should have taken hundreds or thousands of miles more. Or think about it in terms of a human lifespan. If the universe's age were an 80-year life, 280 million years corresponds to about 1 year and 7 months. MOM-Z14 existed when the universe was a toddler, barely walking, barely talking, and somehow that toddler had already produced a galaxy with 100 million stars and chemical enrichment that normally takes the equivalent of decades. The raw fractions say it most simply. 280 million years is 2.03% of 13.8 billion. When MOM-Z14's light was emitted, only 2% of cosmic time had elapsed. 98% still lay ahead. The light from MOM-Z14 has been traveling for 97.8% of the total age of the universe. And just 100 million years before MOM-Z14 existed, roughly, there were no stars anywhere, only darkness and neutral hydrogen. In the cosmic blink of an eye, something built a galaxy containing 100 million suns with supersolar nitrogen enrichment. However, the universe did this. It did it fast. There is one final thread to pull on, and it brings the story full circle. Naidu's paper on MOM-Z14 draws a connection between its chemical fingerprint and the abundance patterns in the Milky Way's oldest globular clusters. This is not a casual analogy. The nitrogen to carbon and nitrogen to oxygen ratios observed in MOM-Z14 fall in the same range as the anomalous abundance patterns in globular cluster stars that have puzzled stellar astronomers for decades. Those anomalies have been attributed to enrichment by a hypothetical first generation of supermassive stars, objects exceeding 1,000 solar masses that formed through runaway collisions in dense environments and then enriched the surrounding gas before a second generation of lower mass stars formed from it. If MOM-Z14 is indeed a proto-globular cluster environment, then what JWST is showing us is not just the most distant galaxy. It is the actual formation site of the kind of structure that still exists, still orbits, still can be observed in our own galaxy today. The globular cluster Omega Centauri, for instance, is visible to the naked eye from the southern hemisphere. It contains roughly 10 million stars and is thought to be the remnant core of a dwarf galaxy that was consumed by the Milky Way billions of years ago. Its stars show the same kind of abundance anomalies that MOM-Z14 spectrum displays. If MOM-Z14 is a proto-Omega Centauri, or something like it, then the faint red smudge in JWST's infrared detectors and the bright ball of ancient stars visible to the unaided human eye are the same kind of object, separated by 13 billion years of evolution. That is a staggering connection. It means that the mystery of MOM-Z14 is not just about the early universe. It is about our universe. The structures that formed in those first few 100 million years did not disappear. They evolved. They were consumed by larger galaxies. They were stripped and rearranged and incorporated into the structures we inhabit today. The globular clusters of the Milky Way carry within their stellar chemistry a record of conditions that prevailed in the epoch of MOM-Z14. They are fossils of cosmic dawn embedded in our own galaxy, and JWST may have just shown us the quarry where they were carved. Naidu seems to understand this. His paper's language, connecting galaxy evolution across the entire sweep of cosmic time, is not the language of someone reporting a data point. It is the language of someone who grasps the full narrative arc of what the data implies, from the first dense clusters of supermassive stars, burning through the primordial fog, forging nitrogen in reactions that should have taken hundreds of millions of years, to the ancient globular clusters that orbit the Milky Way today, carrying that same chemical signature like a serial number stamped at the factory. 13 billion years of continuous history, bookended by two observations, one from JWST and one from a backyard telescope. And the central question, the one we opened with, remains stubbornly, gloriously open. What is the early universe trying to tell us that we do not yet understand? We know it is telling us that galaxies formed faster than predicted. We know it is telling us that chemical enrichment happened on timescales that strain conventional stellar physics. We know it is telling us that large-scale structures assembled earlier than expected. We know it is telling us that the very first stars may have been more exotic than any we have ever directly observed, possibly including objects exceeding 1,000 solar masses that forged nitrogen through mechanisms that left fingerprints still visible in our own galaxy. We know it is telling us that the process of reionization may have started earlier and moved faster than models suggest. We know it is telling us that the infant universe was not the simple, sparse, slow-growing place our models described, but something faster, brighter, more chemically complex, and more structurally diverse than we imagined. What we do not know is what all of this means. Not yet. And that not yet is itself worth sitting with for a moment. Science, real science, spends most of its time in a state of not knowing. The popular image of science is one of discovery, of eureka moments, of puzzles solved and mysteries resolved. But the actual lived experience of science, the day-to-day reality of people like Naidu and Bunker and Boylan-Colchin and Finkelstein, is mostly uncertainty. You collect data, you analyze it. It tells you something you did not expect. You propose explanations. Most of them turn out to be wrong or incomplete. You collect more data. The cycle repeats. The intervals between genuine understanding can be decades long. Quantum mechanics was formulated in the 1920s, and we still do not agree on what it means. General relativity was confirmed in 1919, and we still cannot reconcile it with quantum theory. The history of physics is a history of productive confusion, of sustained engagement with problems that refuse to yield to easy answers. The impossible galaxies are the newest entry in that tradition. 3 years of data, dozens of confirmed objects at distances nobody predicted, chemical signatures that defy conventional stellar evolution, structure formation timescales that strain the best cosmological model ever built, and no resolution in sight. Not because the community is not working on it, they are working furiously, but because the problem is genuinely hard and the data is genuinely surprising, and the universe, as always, is under no obligation to make itself easy to understand. What we can say with confidence is that JWST has changed the field of observational cosmology more profoundly in 3.5 years than any instrument in the previous 2 decades. The questions being asked now about the early universe are fundamentally different from the questions being asked in 2021. Before JWST, the question was whether we could find any galaxies in the first few 100 million years. After JWST, the question is why there are so many why they are so bright, why they are so chemically mature, and what physical processes could have produced them. The question has flipped from, are they there, to how are they there? That shift from detection to explanation is the signature of a paradigm in transition. And it is worth remembering that the last time observational cosmology experienced a shock of comparable magnitude was in 1998, when two teams independently discovered that the expansion of the universe is accelerating, driven by what we now call dark energy. That discovery also came from data that defied the existing model. It also produced years of debate about systematic errors and alternative explanations, and it eventually led to the current Lambda-CDM model that JWST's galaxies may now be challenging. The pattern repeats. The universe surprises us. We argue about what it means, and eventually, if we are honest and persistent, we arrive at a deeper understanding than we had before. Boylan Colchin, who has been one of the most thoughtful voices throughout this entire saga, framed it precisely. Those are the best problems, he said, because no matter what you get, the answer is interesting. If the explanation turns out to be purely astrophysical, if bursty star formation plus AGN plus modified IMFs plus some as yet unmodeled process can account for everything, then we will have learned that galaxy formation is far more complex and dynamic than we thought. Our simulations will have to incorporate physics that we have not yet modeled. Our understanding of how stars form and evolve in extreme environments will need revision. The textbooks will have to be rewritten, not to add a new fundamental force or a new particle, but to add chapters on the explosive, volatile, creative physics of the first few 100 million years. If the explanation requires changes to fundamental physics, to the nature of dark matter, or to the cosmological model itself, then we will have learned something even more profound. A 25-year-old cosmological model that passed every previous test would need modification, and the modification would open entirely new questions about the fundamental architecture of the universe. Either way, we learn. Either way, the universe has taught us something we did not know, and either way, the answer reveals something about the cosmos that was hidden from us before July 2022, when the golden mirrors of JWST first focused the ancient light and the impossible galaxies stared back. 3 years ago, the James Webb Space Telescope opened its golden eye and looked at the darkness between the stars. It found light where there should have been none. Too much light, too early, too chemically rich, too structurally coherent. It found nitrogen that should not exist in a galaxy from 280 million years after creation. It found a collapsing megastructure at 1 billion years that should not have formed for another 2 billion. It found, in the words of Boylan Colchin, fossilized rabbits in Precambrian strata. The rabbits are real. They have been confirmed spectroscopically, measured chemically, catalogued statistically. They are not mirages. They are miracles in the specific and deliberate sense that Naidu chose when he named his survey. The question was mirage or miracle. The universe answered, and a 30-year-old poet from Hyderabad, standing at the end of a chain of human connections that stretches from Pascal Osh's office at Yale to Andrew Bunker's 2 decades of instrument design at Oxford, to Boylan Colchin's elegant mathematics in Austin, looked at a faint red smudge in the data from a telescope 1.5 million kilometers from Earth and saw, possibly, the birthplace of our own galaxy's oldest stars. The most distant object ever observed, carrying a chemical fingerprint that matches the most ancient structures in our cosmic neighborhood. A galaxy from 280 million years after creation, speaking in the language of nitrogen and carbon and starlight, saying something we do not yet fully understand, but cannot ignore across the entire sweep of cosmic time. From the first dense clusters of impossible stars to the ancient globular swarms visible in our own night sky, one continuous thread, 13 billion years long, connecting a faint infrared smudge to the stars above your head. The universe was in a hurry. We are still trying to figure out where it was going,